Hello students. The purpose of this supplementary video is to review the Moivres Theorem and root of unity. I had several questions from students and I sensed that, not enough exercises basically. I sensed that there are some lack of understanding prevalent among students, so I took care of it in class. Now I must do the same thing to online students. Here we go. Basically what we want to do is this. To find out a general algorithm to solve complex equation of this kind of form. Z to the nth power is equal to W, where Z and W are complex numbers. What we use? We use the polar form and the Walrus Theorem. Theoretical background for the Moivres Theorem is this and that. If you multiply two complex numbers expressed in the polar form, we multiply the moduli and add up the arguments. If you divide, then we divide the moduli and we subtract the arguments. The proof is rather simple. All you have to do is just fold them over and then simplify and apply the sum and difference identity for sine and cosine, and here we go. For division, it's a little bit harder because we'll have to realize the denominator by multiplying the conjugate of the denominator both to numerator and denominator. But afterward, it's nothing more than just simplification, taking the like terms together and then applying the difference identity for sine and cosine. Applying those multiplication principle and the addition and the division principle multiple times, we get the Moivres theorem. Kind of like this. Z is r times cosine of theta plus I sine of theta, and multiply those together. What do? R times r, we get r squared, and then we have to add up the angle, theta plus theta. That generates r squared times cosine of 2 theta plus I sine of 2 theta. The right hand side when n equals to 2. Now repeat it. Z cubed is z squared times z. Z squared is this, as we just proved, and then multiply another z. What do you get? R squared times r is r cubed. Okay, that part is the modulus. And then add up the angles, 2 theta plus theta. So the argument is 3 theta. What do we get? We get the right hand side for n equals to 3. Repeat it once again. R to the 4th power, z to the 4th power is z cubed times c. Multiplying by moduli, we get r to the 4th power. Adding up the arguments, we get 4 theta. We can repeat it multiple times, no matter how many times, and we end up with the right hand side for arbitrary integer n. What if the integer is negative? Well, I didn't write down everything here. It's basically applying the division principle over and over again. Subtract over and over again. Now let's apply the Moivres theorem, this one, to this kind of problem. This is a problem we did. Z to the 6th power is negative 64. So we'll choose another problem. Let's go with this one. How do we handle something like this? The very first step is pretty much straightforward. We want z to the 8th power equals to something. Z to the 8th power is equals to a certain complex number. And what we want is the polar form so that we can apply the Moivres theorem. So step 1 is to change everything into polar form. Once that's done, we go over to step 2 and apply the Moivres theorem. By the way, I wrote down general algorithm here. Express Z and W in the polar form. When W is r cosine of phi plus I sine of phi, then we can find out this capital R, the modulus of this right hand side, by this usual method, square root of x squared plus y squared. And then argument, again the usual method, arctangent of y over x when your point is in first or fourth quadrant. pi plus arctangent if your point is second or third quadrant. That gives you the polar expression of W, and that's going to be step 1 of the problem. Let's go back to our problem here. Step 1 is to express the right hand side in the polar form. How do you do that? Let's first find out the modulus. Square root of this one squared plus that one squared. And we end up with, well, this computation. Capital R is square root of this one squared plus that one squared. Turns out square root of 64. We have 8. And then let's find out the argument, angle phi. And we get arctangent of y over x. But then again, in this particular case, x value is negative and y value is positive, so we end up with a point in the second quadrant. When x is negative, when we have second or third quadrant, you have to point to the other way around, so we have pi plus arctangent. Consequently, what do you get? Pi plus negative pi over 6, we end up with 5 pi over 6. In short, we ended up with this equation, z to the 8th power, which is that, but in turn it is equivalent to 8 times cosine of 5 pi over 6 plus I sine of 5 pi over 6. Now we are ready to solve this equation, but before that we have to express z as a polar coordinate as well. What if we do that? It will be r times cosine of theta plus I sine of theta to the 8th power is equal to this right hand side, isn't it? Okay, and then if we apply the Moivres theorem, this is what we are going to get. R to the 8th power, and by the Morris Theorem we need 8 theta there, and the right hand side as you see over here. Now compare the modulus and the argument. Excuse me, I lost my control of mouse momentarily. R to the 8th power is equal to 8. Therefore R is 8th root of 8. And what is 8th root of 8? Well, we have Mathematica here, so let's find it. Approximately it is, well, this number, but that number is not really that important. 8th root of 8 is precise expression, and that'll do it. Now how about the argument? 8 theta is equal to 5 pi over 6. Consequently, theta is equal to 48. 5 pi over 48. And we are going to get a solution like this. Z equals to R times cosine of 5 pi over 48 plus I times sine of 5 pi over 48. We found a solution. Is that complete? I'm afraid not, because the original equation is, well, polynomial equation of degree 8. So we need 8 complex solutions. We only found out one solution here. Where are the other 7 solutions? Something has to be done. What is that something? The periodicity plus 2k pi. Let's go back to this general algorithm. Now I include it here. First, you have to express the W, the right hand side, in the polar form, and polar radius and the argument. You can get those. And then, in order to apply the Moivres theorem, z to the nth power, or r cosine of theta plus I sine of theta to the nth power, is not just capital R times cosine of phi plus I sine of phi, but we need this 2k pi. If we do not take nth root, then this plus 2k pi doesn't do anything, because by the periodicity of the angle we have the same position. But if you apply the Moivres theorem, and the left hand side becomes n theta, and then solve n theta is equal to phi plus 2k pi, theta equal to phi plus 2k pi over n, all of a sudden we have n different solutions. You have to plug in k equal to 0, 1, 2, all the way up to n minus 1. If you plug in n, that's going to be the same as plugging in 0, because if you plug in n, then 2n pi over n is the same as 2 pi. So 2 pi revolution, we come back to the same place. Let's go back to the original problem we had been working on. So these are not complete solution. No. And let's move on to step 2. Here we go. This polar expression to the 8th power is equivalent to, well, polar expression of this right hand side we found out, including 2k pi. And then if you apply the Moivres theorem, and we have this left hand side, r to the 8th power, and then angle with those 8 theta turns out to be the right hand side. Comparing the moduli, we get r to the 8th power is equal to 8, and r is 8th root of 8. I don't care too much about that numerical expression of 8th root of 8. This is sufficient. Now let's compare the moduli. 8 theta equals to 5 pi over 6 plus 2k pi. So if I divide everything by 8, we end up with 5 pi over 48 plus 2k pi over 8. Taking the common denominator, we get that. In other words, the polar expression turns out to be, as a matter of fact, we can just put this one in place of r right away. Where the polar angle theta, or the argument theta, is obtained by plugging in k equals to 0, 1, 2, 3, all the way up to 7, generating 8 different solutions. This is a general way to solve a complex equation of the form z to the nth power equals to w. First, express it as z to the nth power equals to w. You may regard it as step 0 or something like that. And then step 1 is to express the right-hand side in the polar form, and that is itself a problem. You have to find out the modulus capital R using the formula square root of x squared plus y squared. And then you have to find out the argument using arctangent of y over x, or pi plus of that, depending upon the x coordinate value. Eventually you get the polar expression of the right hand side, but do not forget plus 2k pi. And then if you compare the modulus and then the argument, then you're going to get the solution. Modulus part is easy here, and we have all the angles there. Geometrically speaking, all those solutions must come along a circle, forming a circular symmetry, and that's why polar coordinates and polar forms work better than rectangular coordinate system. Let's see. Here is the full solution in the same viewing window, or the single viewing window. Barely made it.